Great. So far we looked at the embedding lookup approach of user representation, user ID representation, and we also looked at the deep hash embeddings approach, which somewhat magically does not have any memory explicitly per user ID, but the multiple neural network layers, starting with a deterministic hash, learns to find and end up with an embedding which is, according to the paper, equally performant with the ID lookup approach, and saves a lot of memory. Again, our focus is kind of neither. We are not going in this DHE direction. We're just taking inspiration from it. That stack layer of MLPs can generalize and yet perform at a level close to memorization. The thing that will change is the input to the stack layer of MLPs. Instead of it being a deterministic hash function, in our proposed approach, we will use user features, and we will try to learn what works for a user cohort or user cluster. Okay, so this approach is slightly different than the previous ones. If you remember the first one, it tries to learn exactly what is this user's interest. Right? This also tries to learn that, again, through a different mechanism. Here, we are learning which cohort a user is closer to. So this entire machinery, and I'll explain it in a little bit, but looking at user features, we try to see which cluster of users this user is close to. And then for that cluster of users, we try to learn what is, we'll try to learn the right embedding. Okay, again, we use the DHE layers for modeling that specificity, but the input is constructed in a way that a group of users, sometimes many thousands of users, kind of map to the same index in this cohort embedding table. Okay, so let's look at the implementation. User cohort embeddings. Again, apart from the init function, which has the required initializations, the only change is the get user embedding. If you see, the common pattern in all of our code is that multitask estimator implements everything, and then the deep hash embeddings, the user cohort embeddings, and later on we will look at mixture representations. All of those only focus on the get user embedding function, the user ID lookup as well, the get user embedding function. Okay, so now let's come back to user cohort embeddings. So as you can see here, the user ID is not used. It's not used here. We are only looking at user features. Now, based on that, there's this cohort addressing layer, which tries to say among the H user cohorts. H can be, let's just say, 2,000. It's not, even if you have 5 billion users, the space of H is much, much smaller than potentially your user count. And maybe there is some number you can think of. I believe in clustering literature, they recommend square root n as a good size. I'm not very well versed in that, but suffice to say, it's a smallish number, and you can experiment with the number. So this H is, let's just say, for our purposes, 2,000. Okay, so the cohort addressing layer comes up for each user. That means each row in the batch, it comes up with a value per cohort. So for this user, what is their affinity, so to speak, for each of those cohorts. We'll look at top K regularization later. Let's assume it's disabled. And then it, using a matmul, it multiplies with the embedding matrix, which for those 2000 users, 2000 cohorts, it has a specific embedding vector. So BH into H DHE in goes to B DHE in. Okay, and then you have the multi-level stack. So come back. So for using these user features neural network, you come up with an affinity per cohort. There are H cohorts, so an affinity value per cohort. And by construction, we'll make sure these affinities are non-negative, 0 or higher. And then we can multiply it with the cohort embeddings and use that. Okay. The top K regularization that I was talking about essentially is that, hey, can we limit it to the top K? Maybe K is 1, so top 1 regularization of this. And also this neural network that comes up with these cohort affinities, you should and you can have dropout during training so that the backprop from the user, from each user, is not just going to, like it's not very concentrated due to dropout. You will hopefully learn, like in that user will be able to influence more than one cohort. Okay, so the basic idea is that let's imagine that you cluster users, and for each and these clusters are set up in a way that naturally due to your model learning maximally with whatever parameters it has, these clusters be set up in a way that they will be distinct from each other, and they will try to learn what works in their cluster. Okay, if you want to set up some sort of incentive for these cohorts to be distinct, remember dropout actually is not an incentive. It prevents this. It prevents, like, it makes sure that some clusters are similar to other clusters. So it's a little bit of a generalization in that sense. But if you want to incentivize your cohorts to capture different things, you can always try to have like a loss that captures how similar these cohort embeddings are. Okay. So coming back, you look at this cohort. Let's look at this cohort addressing layer. Cohort addressing layer. It takes the user features and outputs. The edge, this we called edge in our diagram, one value for each point in the cohort table, and drop out, like we mentioned. Okay. Now, one thing you could do is to have softmax here. So this cohort affinity right now, it does not. It could be negative, but we could add softmax here to ensure that the output is somewhat like a probability.